Okay, Doug, are you there? There's a little bit feed. Looks like. I don't know if Doug's there. Are you? I think he's trying to fix his audio issues. But anyways, we should get started shortly after he joins back. Are you there, Doug? This is already done. That's a lot of echo. I'm speaking, but I can't hear you, and there's a lot of echo. Are you fixed it yet?
Turn it up, okay?
Are you there? I can.
Is that better?
Let the people in the chat decide.
Okay, yeah, why don't you do that? We should get started, so, you're going to do the most of the talking, so I'll just, change targets as we go along.
Yeah,
maybe you should do the welcoming.
We're already streaming. It's already started.
Okay. All right. Well, let's get to it. So I don't know if people can hear me. This is Doug Solisey. If you think they can't, it would be nice if you gave a welcome.
Yeah, people are entering the chat, so I think we should talk about. Well, yeah, there's still echo from your speaker. I can't tell.
But you can hear me.
Yeah, I can hear you, but when I speak, it's going through your speaker, and your mic's picking it up.
Okay. Well, maybe I need to. Okay, how's that? Is that better?
Let me see. Yeah, I can still hear myself.
Well, maybe it's just a defect of this headset. I don't know. I mean, the earphones are should be blocked from the microphone.
Okay, what about now?
Let's get started.
No, everyone in the chat's talking about it. It's not good at all.
Oh, really?
So, how much distance is there between the microphone and the speaker?
The speakers are disconnected.
Yeah, but the speaker on your headphone.
Well, my headphones are, they're headphones. The microphone is it's a little thing that, extends from the speakers down.
Okay, let me. I can still hear myself echo. Let me see.
Well, I can try it. Okay, I can. Hello, keep talking.
Okay, well, the echo's gone now, right? Yeah, let me. Okay, I guess I'll just do the introduction quickly.
Yeah, our apologies. We're having a little problem with the audio, as you can tell. We've got everything else working.
Let me see if it's still out there. Oh, it's gone, I think. It's gone now? Or did he mute it? Well, how about this? So to make it work, whenever, is there much less? I think he can speak then, Doug, so. Or is he muted? Let me see if he's muted. No, he's not muted, that's why it's still there. Okay, well, we gotta get started anyway. Can you mute yourself when I'm talking then? That might solve the issue. Okay, so if you remember I'm just trying to. We got our first image, so I'm just gonna try to do some processing to it. Well, Doug's trying to fix the echo issue. You there, Doug? Okay, I think I hear you.
Yeah, you can hear me?
Yeah, but the echo's still there, so I guess it's fine.
Well, we'll just have to live with it. I don't know what to do about
Well,
it.
if you mute yourself when I talk, then that works.
Okay, then I have to change screens to, okay.
Well, I'm not on your screen all the time, so it's fine.
Yeah. Well, are you going to talk? Go ahead.
Well, how about you do the introduction first?
Okay. Well, I just did. I don't know if anybody heard me.
No,
Can you tell?
nobody heard it. I don't
Okay,
think
this is
anyone.
Doug Solacey. I'm up at Curiosity Peak in Julian, California, and I want to give a warm welcome to everyone who's with us this evening. We're sitting here behind the computer. We've got a refractor here at Curiosity Peak. It's a 115 millimeter refractor and with a color camera connected to it, and we're seeing a star here in the center of the screen, and that star is Omicron 1 Orionis, which means it's part of the Orion constellation. And Vivek's home in San Marcos, he's got a telescope there in his backyard and a spectrograph connected to it, and he'll be aiming, his scope is aimed at the same target, and we're going to be on the same targets all night. So he'll be having the star fall on the slit in his spectrograph, and that will be breaking it up and showing us what the makeup of this star is. So if you have questions, please, or comments, or just want to tell us you're here, we love that. Please use the chat. Just type it in, and Vivek will respond to you. I'm not seeing the chat myself, but Vivek will be seeing them. And if you like what you're seeing tonight and you want to share it with other people, please tell them about our channel, Curiosity Peak Observatory, on YouTube, live streaming, and every star party that we do is archived there and can be seen very easily just by going to the channel and clicking on whichever one that you want to watch. So we've got a very interesting list of targets tonight. It's all stars, but stars that are, many of them are embedded in larger entities out there in the Milky Way, mostly. Pretty much everything that we're looking at tonight is going to be in the Milky Way. And that means there's a nebula surrounding some of these stars, and stars interact with their environment. They're not just out there all, separate from everything else. They ionize and give off light and all sorts of energy, which is reflected, and which can also, when the gas, or we call nebulae, are ionized, they glow and give off light, which makes them very, very interesting, photogenic as well as scientifically fascinating. So I'm going to end my introduction, and Vivek, why don't you take over, okay? I'll mute myself so we don't get any echoing.
Okay, so that means we should have... No, it's your speaker, I think. So you...
Well...
Okay. I don't think so. Don't mute yourself. I think you just have to stop listening, I guess.
Stop listening. Okay. I'll put my hand. I'll put my hand around the microphone.
Okay. Well, let me see if that works. How's the echo now? So we process this image.
Can I close this little item in the middle of the screen here that says please select a camera?
Yeah. You started SharpCat.
Huh?
You started
Oh, I
SharpCat.
did. Oh, I did. Okay, that's the problem. I wondered where that. I thought, okay. Well, I just want to close it.
Alright. Okay, so then we have to get a calibration. There we go. Okay, so we're looking at Omicron 1 Orionis, which is a very interesting star because it has an overabundance of titanium. So we'll be looking at that line. But so what I have to do is just take a calibration frame because spectrographs need a calibration in order to get a proper view to assign wavelengths to pixels. So we're gonna start that. And meanwhile, we have Doug. You need a close fire capture.
How do I get it to close? I'm trying.
Guess you have to wait. How about you turn your speakers down for now?
I speak. Okay.
Or turn off the headset for now. And then replug it so that the echo stops. Okay, I think that worked. Yeah, it worked. Okay. So we're getting there with the calibration frame. Yeah, because Doug disconnected his headset for now. So hopefully that fixes the audio issue. So I just have to now run it to the program. Eh, that didn't work.
You help me get.
I didn't hear that. Sorry about all the audio being a little problematic. Oh, this thing's plugged in again.
Green is.
Are you still there?
I can't get rid of fire capture. This partially blocking the screen.
Let it load. It should then it should go away.
It's searching for a camera, which it's.
Well, I don't know what's happening on your.
Okay, it's gone.
There we go. Okay. Let me try to get this done. It's still working? Oh no, the echo's still there. me try to. Alright. Alright, let me see if that works. Okay, that's been like 20 minutes. Still there, Doug?
Yeah, I'm here.
Well, the Doug. Okay, well, this is being a little problematic. Let me try this. Okay, can you cover the star while I'm try to get the spectra process?
Sure. Do you want to? Should we stay on this star, or should we move on?
No, we can stay on the star.
Okay. I don't know if people can hear me. I don't know. My commentary is going beyond you and I. But
Yeah, people can hear you. It's just that I have echo.
Okay. All right. Well, as I said, this is Omicron 1 and Orion. It's right in the center of the screen, and it's a binary star, which means that it's a system actually of two stars that are orbiting around a common center of gravity. Depending on where that center of gravity is, depends on which star has the greatest mass. The center of gravity will be closest to that star, or maybe even inside the star. So this is in the constellation Orion, and we're going to be looking at numerous things in the constellation Orion. In fact, the first, I think, 6 stars we're going to be looking at are all in Orion, and they're stars that are, some of them are embedded in nebulae and have a profound effect on the neighboring nebulae, the clouds of gas that Orion is known for. If you look up at the constellation Orion, which is to the south and more or less, I guess, in the halfway between, maybe not quite halfway from east to west, you'll see Orion's belt. And I think Alnilam is one of our targets that's right in the belt,
Yeah.
the center of the belt. And Rigel is the bluish star that is more or less like the foot of the hunter, Orion. If you have binoculars or just go outside with your naked eye, you can see Orion. Orion's probably the most striking constellation, I think, without a doubt, in the winter sky. It's got, Rigel and Betelgeuse are both very bright stars, two of the brightest stars in the night sky, and certainly two of the brightest stars in the winter sky. The big difference is Rigel is more blue, and Betelgeuse is more red, or to your eye it will look a little orangey. And Betelgeuse is in the upper left part of the constellation, kind of where Orion, I think he's holding up a spear or a bow or something. So that's kind of the upper part of his outstretched arm, and then Rigel, the bluish star, is kind of down where his foot would be, his right foot, I guess. Or if you're looking at it, the constellation would be on the right side. And we'll be seeing the spectra of those stars, which will reveal, what a little more profound way how different they are. And we're going to look at some other stars in Orion too, and we'll see some other very interesting nebulae that are in this neighborhood of those stars. In particular, Alnitak is one that's quite well known. If anyone's seen the nebula, the Horsehead Nebula, it's pretty close to Alnitak, I believe.
Yeah, once I get this thing working.
Okay, having a little difficulty with the spectrograph.
Well, I was focusing a little bit on the audio, so that was a bit.
Yeah.
Oh, come on.
As you might imagine, putting this on requires getting a lot of technology to work. a lot of components that need to work at the same time, whether we're talking about...
with the spectroscopy's code too.
Yeah.
So
there's
that's the thing.
Huh?
No, code 2, so... Alright, let's see.
What's involved actually in just getting the star on the screen that you're seeing right now means having a telescope, which is
they're not
automated.
they're not seeing a screen. Right now they're seeing the code. That's been going on. Because I'm just trying to get this to load finally.
Okay. Yeah, I was just talking about how all this works.
Yeah, I know.
We have a telescope on a mount up here in Julian, and the telescope is tracking, which means it's following the star, the target, which is in itself an accomplishment since the Earth is turning. And as we all know, the sky appears to be moving, so telescope has to compensate for that. In order to have a crisp, sharp image that's not where the stars aren't, looking like hyphens or worse, it means that it has to follow very accurately. So it has an additional camera besides the one that's taking the pictures of that area of the sky, just in order to kind of give feedback to the mount, the telescope mount, and make very small corrections to keep it fixed right on the target. And these are what you're seeing right now on the screen is actually 120-second exposure. In other words, 2-minute exposures. If you went outside with a camera and pointed it up at the sky and started exposing for 2 minutes, the stars would trail, very noticeably. And that's what would happen too if the telescope wasn't being guided right now. So that's part of the deal. And then we have a computer that's downloading the images that are coming from the camera. It's a CMOS camera, obviously a digital camera. And as those images are downloaded to the computer, they're put up on the screen. So these images that you're seeing right now are not images that we're saving. These are strictly for live viewing, but they give a pretty good picture of the sky, especially since it's a color camera, just like your typical DSLR camera that you take a picture and boom, it pictures in color, right? We kind of take that for granted, but it involves a pretty complicated little sensor that can detect the different wavelengths of light, and then the camera combines them together, and the computer helps it do that and produces a color image.
Yeah, right now they're just listing the code. I'm trying to generate the graph.
Okay. It's
just right now the typing stuff and the file not found errors. So yeah.
Just so people know, spectroscopy is not. Yeah.
Well, it's good that people are still hanging.
Yeah, we appreciate that. just to give you a little perspective, spectroscopy is not a very typical activity among amateur astronomers. There are some who do it. Obviously, Vivek is one of them, but it's really something that's more going after the science. Most of us who are in amateur astronomy, we share the wonder and awe of looking up and the beauty, and that's where the cameras and observatories. All right, you got it. Good. So we enjoy the beauty and the wonder of what we look at and the images that we capture. But some of us amateur astronomers go even further than that and get into the science and do use our setups for scientific investigation, which is what Vivek has been doing for a few years now. And so anyway, we're really lucky to have him here with us and sharing his knowledge and experience of doing this. He's going to be going away to university later this year, so he won't be in the San Diego area, but we'll be probably in touch, and who knows, maybe we'll be able to do some more of these events remotely, because one of the things that we're doing these days, as is everyone, because of COVID, is we're doing a lot of things remotely, especially things that involve collaboration. So it's kind of pushed us to do these virtual star parties, since we can't do them in person, at least for the moment. And so we're getting deeper into the technology, but with that comes challenges. So appreciate everyone hanging in there. It'll be worth it.
We have
believe
it.
me. Yeah, got it? Okay.
Finally.
All right.
That took a while, but we got it.
Okay, the spectrograph has started to behave itself.
Okay, so now I can talk about... So let me talk about what this is. So the reason why we're even on the start is because this star is very barium rich. There's also titanium. Well, we'll get to that a little bit later. But so this is the star. It's a little more cooler than the other stars. So you can see it has more of an orangish color here in the camera. So now when we look at the spectrum, which is finally loaded, you can see the barium line over here. So this little absorption here is the signature of barium, which is a very unusual element to see in a star. Oh yeah, Doug, can you unplug your headset?
Unplug it completely?
Yeah, I'll talk to you through the phone.
Okay, sure.
Because it's echoing really badly.
Okay, yeah, I can do that.
So no echo now? No? Okay, now it's not echoing. So we have the barium line, which hopefully people can see here as a little indentation. This is a spectrum. There's a lot of the reason why there's so many ups and downs here is one, because it's fairly noisy, and the other part is because there's a lot of metals in the star. It's got an unusual abundance of metals. So here in particular, this is a signature of barium. This little indentation here. So this is going to be the general trend of what we're doing now. Finally, after like around 30 minutes, but at least we've got it working now. So now we can swing around to a different wavelength of the same exact star and take a look. So let me swing it to 4886. So this will be a little trip. So now I just have to adjust where it is. That's going to be at approximately, let me look at this, 15.65. Okay, we're there. So if you notice here, we got a little bit of spectrum. It's just a little unfocused, so now I have to focus it. Okay, alright. Let's get this. I'm sorry for subjecting everyone to a lot of code, but that wasn't working very well. Until I finally got it working. Doug, is your audio off? Well, that's disappointing. Okay, now it's... Hey. Is it still echoing? Yeah, it is. Let me try to see if your speaker is doing something. Oh, it is doing. It's your monitor. Doug, it was your monitor the entire time. You can plug the thing back in. Your monitor has been speaking the entire time. Okay, that's fixed now, so you can plug it in. Okay, so now we know what was doing all of that. So now we're gonna try to Yeah, he's not speaking because. No, never mind. See.
Hello?
Yeah. Can you just turn this part down then?
Huh?
Can you hear me? Okay, he can't. Okay, so. So whenever I speak, can you turn this off? The speakers here.
Are you talking to me?
Yeah.
Turn what speakers off? I mean...
Look at I have the speakers at the bottom right. Yeah, there we go. So, okay, now the echo's gone.
Oh, okay, I'll use that. Okay.
Okay, good. Well, that was why it's echoing. Okay. We lost the star for a bit, but we'll get it back. Oh, there it was. Okay, there's the star. That's one Orionus. Come back to me. And I'll start guiding that again. Alright. Start. Then we just had to take a 300-second exposure. And here's the graph officially. This is going to be the general trend for tonight. Okay. So we started a little bit late, so it's okay. Meanwhile, I guess we can talk about some other graphs. I'll wait for that image. Think similar phenomenon.
Well, I'm watching on my phone.
Okay, that might help, but there's gonna be delay.
Only about 5 seconds.
It's feedbacking. Can you stop that? There's a lot of feedback. Like, mute yourself.
Okay.
Okay, okay, anyways, back to what I was doing. Right. Yeah, here we are. So now let's do a small little comparison here. So this star is also another barium star, but if you notice the difference, there's a slight difference between the two, and like this one is more of, there's just a lot of different lines that are just continuous. But if you notice here, there's a little bigger indentation here. So what happens here is sometimes spectra can overlap. So this is actually one very broad line, and this is from the titanium we were talking about. And hopefully when this thing loads, we'll be able to get another much more bigger descriptor for the evidence of titanium. But on the other hand, this line here, I'm pretty sure denotes something called magnesium hydride, which is another special element blend that these stars can sometimes produce. So this is an S-type star, and that's why it has an overabundance of metals like titanium, barium, and weird molecules such as magnesium hydride, and that's what we're going to be seeing shortly. We're still on. So, let's see. Alright. It's recentering. How do you know which absorption line is which element? So, yeah, keep the questions coming because we're going to be waiting a little bit. So, let's talk about what I was doing this entire time, because I think that's really confusing because we were distracted by audio problems and all of that. But so first, we have our image here. Well, it's here now. This is what you're seeing on the screen. This is just the... Oh, well, anyways. Oh, here. Let me open it really quickly so you can see that. So, this is our spectrum. And this is what we just get when we put the camera, we put it in the thing, and we take an image. We put it in the spectrograph. And what I was taking earlier was a calibration thing. So, it looks like this. This is a very intricate process, and this is what almost every spectrograph has to go through. So if you notice, there's these very faint lines here. If you can see that, let me open that a little bit bigger. Let's see. So those are spectrums from argon. That's spectral lines from argon and neon, because there's an argon neon lamp on the spectrograph, and we use those to basically identify where what the wavelengths are. For example, we're around 400,555, which is where the barium line we're looking at is, and we can use this to basically construct that plot, and that allows us to assign pixels to wavelengths, and that's what gives us this cacophony of peaks and valleys. And the reason it's a cacophony is because, like as I said before, there are a lot of metals. Almost every single valley you see throughout this entire thing is some metal of some sort, mostly iron, but sometimes there can be really interesting ones like barium, which is this one right here. And that's what this marker shows. At around 4,554 angstroms unit of wavelength, we have a barium-2 line. And that's the same procedure for this, although this is our data, so it actually looks a little bit better. But you can see that same exact, a little bit, I guess it's not as strong, but it's there, of barium. So that's what we use to identify where this is. And now we're doing a similar thing, and we just got our first, we got this one over here. So let me now take a quick gain. You can take a calibration, another calibration spectrum this time with the argon neon lamp. So I'll rename that. It makes it easier to type in the file name if I rename it, because out of Nina it's just like this string of dates and stuff. So we're still on the same star. We got a little bit delayed by the audio, but I think we'll get some, we'll be able to start right. What is that, Doug? But if you look at this, I guess you can see the spectrum right now. You can, because it's a color camera, this actually has color. So you can see that we're in like the teal part. This is 486 nanometers. And what you see right there, this little indentation is hydrogen beta. So that's the hydrogen line at 486, and that's also a reference point for where we are. And all of these little lines show that. Yeah, but when I turn the argon neon lamp on, there's no more, the guiding can't see any stars, it's just illuminated, so. But so if you, this is a similar spectrum, and it's also a cacophony of lines, but this is like evidence that they actually mean something. So this indentation here is chromium, that one there is from silicon, this one is another chromium line, this one is the big hydrogen delta, so this is around 4,600 angstroms. And this cyan one is from manganese. And this is a general trend you see on all of these. They have a descriptor to them. Okay, Doug's having a mount malfunction, so that's something common occurrence tonight. So I'll let him fix that issue. Okay, so we got a really nice calibration spectrum here. This line here is hydrogen beta, and these are some really beautiful looking argon spectra. So we can now quickly get that through. Okay, I should turn off the calibration lamp. Okay. Better if we name it something. So now we can open this in PixInsight to get them processed, because the way they are, it's not ready to just feed into a processing pipeline. So that's one. I already figured out the darks don't work, so I'm just gonna roll with it. So yeah, I tried to use darks, but they don't seem to be correcting the hot pixels, so but that's the best we can do. So now we have to do debayering because it's a color camera. So when you have a camera, it's usually it's just a monochrome chip with filters overlaid it. So in order to make it back into color, we have to do debayering, and that's what gives us this very nice image. Although it's a little orange, but okay. Magnifier. It's not BB stuff. Okay, so this is our spectrum. we'll do the same exact process to it, and already figured out the darks don't work, so we're not going to do dark subtraction. And I'll finish that. And there's our nice spectrum. But this name isn't a very nice name, so we're gonna give it a better name. This is still OMI or minus, but with titanium instead, because that's what we're gonna be looking at. And now the way I have it, it has to be grayscale, so we're gonna do that. That's something I forgot earlier, and that's why we had a little bit of issues, but now I have it covered. And now we're gonna save this. And if you notice, there's a lot of hot pixels, but doesn't seem we can do much about that right now. So we're gonna save this. Okay. And 16-bit, that means that's how many bits are assigned to the image per pixel. And we'll do the same thing with this calibration spectrum. And if you already noticed, this is how intensive spectroscopy can get. And now we're gonna save that. And yes, 16-bit again, and saved. Okay, we can't have two things in here, so we're gonna remove one. So now we can feed the code. Directory of that is should have that copy and pasted already. Snapshot RNE 1.fits hello or yes, and this we're gonna bin because these are very noisy images. So that means we basically add up pixels to downsample in order to get a better signal noise ratio, less noise to it. So we're gonna do that. Mean, and we want it to be lines, you don't want it to be dots because it's too noisy for that. Not going to indicate anything. Okay, so this is basically the pipeline. Now, here's the calibration spectrum that we were talking about earlier, the one that looks really nice. But now we have to tell it what wavelength is that, because otherwise it has no idea where it is. Because it's not that intelligent, but... Alright, let's get that in. So, first line was... That one was 4,764 angstrom. So this is the unit we're going to be using for wavelength. Usually used. That one was at 4,086, and that one was... So we're going to give it 4,861. The final line was at 4,879.864. Just doing this for precision. And there we go, we got a nice fit. So basically all the dots are on the line, so that means I didn't screw up the line measurement. And please give me a graph. Ah yes, we got a graph. So here's our very nice graph. That's hydrogen beta, as noticed earlier. And now the lines we were looking for. So the titanium is this one over here. It's at the very end, but it's this one big aggressive line here. So I don't have that marked, but that's our titanium oxide. Oxide, it's not just titanium itself, it's titanium with oxygen. That's something that's kind of strange, but that's what the phenomenon is in this star. Over here we have magnesium hydride. It's this one little kind of boxy spectral line. And the reason why I can identify this without the markings is because I've taken spectra of this star before. So I'm kind of familiar with how it's supposed to look. But we've got these two unusual molecules back here again. And this one's just hydrogen. So that's more familiar. So I guess we can now move on to what was supposed to be our second target. So actually, is he on Betelgeuse? I think no, he's not on Betelgeuse yet. Let me... Actually, on second thought, let's head to... I think we can make it to there. Okay, what's... Are you there, Doug? No, I can't hear. I don't think you can hear me. Okay, well, I'll just head over to All Attack. So that means we just have to... We have preset target stuff here, so we can use that. Yeah, I don't want that. And then that's not. So don't do that. I'll now head over to that star. Well, let me see if it actually made it. Are you there, Doug? Oh, I can't. So you can still trying to fix his mount. Okay, let's see if we actually got Alan Attack in here. So this one is a more peculiar star. Okay, I think that's Alan Attack. So we just have to center it. So if you notice this black line, that's the slit. And the procedure is to basically get the star onto the slit so that we can, measure it. It's usually best if we put at the end of the slit. I think he's busy with his mount. So let's get that center. And it has a guide star on here, so we can use that. So works. Right, there's our star. Just now gotta make it go on top. Ready to guide. If anybody has questions, I guess Doug is still having some problems, so we'll wait for that. Okay, started. So now this shouldn't take a lot to do. You could probably just do like, this is a very bright star, so we can probably just get away with 60 seconds on it. Don't want it to move. So let me see if he's on in there. No, he's still on Omicron. That's weird. So what this is doing right now is basically tracking this star here to make sure that the star stays centered on the slit so we can get the data on it. It should be 13 seconds left. Oh, I didn't change it. Okay, well that's silly. I'm aware. You just got freaked out that I turned it on. Making it ring. Okay, there we go. So that was what was supposed to be at. We're at hydrogen alpha because the feature that we're looking at is going to be used in hydrogen alpha. Yeah. Oh, wait. We didn't center it back on the guide star. Okay, so we have to get it back on the slit so we can get data on it. Alright. And there we are. Now I can activate this. Okay. That's... Okay, he's guiding on something. Thanks for sticking around. It's been a moment and a half. But hopefully this will be interesting. So Alnitak, it's a star in Orion's belt. So it's right next to the horse head. So if you were in the previous star party, it's there. And what's interesting about it is it has a shell of gas around it, and we're gonna see evidence of the shell of gas, and I'll explain why exactly that is evidence for it being gas. So let me. That's weird. Oh, that's what happens when you don't have it exactly centered on the slit. It's a little bit, it gets dimmer. The farther you are from the slit, the dimmer the resulting image gets. So let me try that again. Right, let's see. It's almost there. Okay. Let me actually take a look and see if we're actually centered on it, because it'll show up in here, hopefully. That's a bit dim. This is a seal, so let me actually get a photograph of it. It's somewhere in here. No, that's not accurate. Oh, it's in here. So this is the setup. Let me just get that started before. Okay, so this is the setup we're using, and it's working fine tonight. Everything else on the software side is being a little bit tricky, but so this is basically a C11. It's on the equatorial mount, and this is an 11-inch Schmidt Cassegrain telescope. And all I've done is attach this spectrograph with a cooled camera on the spectrograph and the guide camera. So this video feed here of the Alnitak is coming from the camera over here, and the spectra we're trying to record, attempting, is from this over here. And basically, whenever I do the calibration spectrum, there's a switch here, and I turn it on to turn on the lamp. And this silver knob here is how I basically set where the wavelength is of what we're examining. So right now I have it tuned to where hydrogen alpha is, and it's aimed at Alnitak. And we're attempting to get a spectrum that's high SNR, and we just did, so that's good. Now the next step is to do the calibration part, and hopefully I can get away with the shorter exposure time this time. So what I do is just switch, and it should turn that on, and then I can do that. And the guiding goes crazy because it's now full of light from that lamp, so let me just do the same procedure as before. We're going to don't need that. This is full of stuff. Don't need any of this. So we're gonna just put that in the folder, because I'm using this folder for where it's gonna be. So we're gonna open this image up, and we're gonna do the processing again of making it a color image and then making it a monochrome image again, because the Bayer matrix is it's not good for doing spectroscopy with, because you got filters attached, and that's not particularly a good thing. So we did that, and we just make a grayscale again. Then this is a terrible name for an image, so we're gonna give that Alnitak. So then we just save that. Not here. There. Don't need that. Save that again. Why does it keep going to the same? Okay, yep. Yes. And saved. So now we're going to do the same thing to the calibration spectrum, which should have showed up. There it is. So this big line here is hydrogen alpha, and that's what we're going to look for on a star. So that will be interesting. Okay, debear it. There we are in color, and now we're putting it back. And that's a terrible name, so we're gonna give that a better name. I think that goes back. Let's keep that. Try that again. Why does it do that? Yeah, I don't want the process console. Yeah, there we are. Back here. finally. Save. 16 bits. If it's any other bits, it becomes harder to deal with. So, yeah, I get it. So now let's do processing. And yeah, this is not typical processing. It's just not you get the graph. You have to make the graph, and that's an extensive process. To control that again. I think I'm using Control C a lot. All right, got it. Light. Snapshot. Name that RNA2.fits. Yeah. Yes, of course I need to mean. We want lines, and we don't want that. Okay, so we got a very nice SNR. That means we've got good data. So now I just have to figure out what these lines are. So I'm going to look at a reference. I know what these are now. And then I just label them. So the first one was 6,532. Then we have our star at HA. And finally we've got that other neon. Good calibration. Now give us a good plot. Huh. Save it. See if it saved it. Oh, it did. Okay, let me. Oh, different file folder. Alnitak. So this is Alnitak now, and now we can see what's different about this. And so we got the helium line over here. This is a big, broad helium line, and what we have here is this is the alpha line, and it looks pretty peculiar because it is. So we have an absorption here, and we have this emission here. So basically, hydrogen atoms are absorbing light and emitting light simultaneously. And usually it's stars that absorb light. And what usually emits light is gas. So what we're seeing here is there's a star, of course, it's Alnitak, and then we're seeing some emission, and that's due to the gas around the star. So what this profile is telling us we've got gas around the star. So the star is expulsing gas from its outer layers. And that can tell us a lot. And looking at the profile of the spectra, that can tell us where that gas is, how fast it's moving, and what the size of the gas cloud is. And what we can tell from this is it's basically orbiting the star, and we're sometimes seeing. And depending on how this profile changes, we can see when we're sometimes seeing the gas cloud, when we're not. So when this spectral line sometimes becomes just an absorption line, that just tells us we're only seeing the star. And when this emission line here comes back, now the gas is visible. And these lines over here, this is some iron lines from Fe iron, helium. So there's a lot here in the spectra, but this is basically what we're trying to look for. So I guess we can move on to the next target. It doesn't look like Doug is. I think he's a bit. Oh, he's there. Okay, that's nice. So this is Alnitak. So we just saw the spectrum here. Looks like that, and now we're gonna see the. Let me go back. Here's the star itself. So yeah, this is the Horsehead in flame, but technically the target we're trying to look at was just Alnitak itself. So okay, good. This is on there. Okay, so actually nobody has any questions, I guess we can move on. See if Michael wanted. I think that'll be good. So let me. I don't know if you can listen. We're moving to Menkawanin, which is a star in Noriga. So you continue the meridian, though. That's problematic because usually that's not somewhere you want to be going a lot. Yeah, I think he's doing it now. Yeah, I can go there. So that's where we're gonna move on now. And this time we don't have to change the calibration, so we don't have to retake one again, so that's a good thing. Just gotta change target. Then we have to put the Menkawanin on the spectrograph. Okay. There we are. Okay, just put that. Oh, went too far. So that's convenient guide star. And now we just put the star on the slit. And we start guiding to make sure that it stays on there. This can be a struggle. Good, it's on there. Now we can... It already started, whatever this was. Oh, that's unfortunate. Oh, stop doing that. Come back. Gotta tell the star we missed it. Please go on the slit now. Almost there. Now I don't click that button, and then we can actually take an image. We gotta clear the directory of images. We'll get this preset. Copy and paste. Now it's ready. Now we got 10 more seconds. I think he's... Oh, he's on the star. So here's the star. It looks like a perfectly normal blue star, but we're about to see why this is a very interesting star. Once this is finished. Okay. We got our spectrum. Let me see if you can see. Okay, I don't think it's quite there, but we'll do some pre-processing now. Just have to do it to the image file because of the calibration. I didn't move it around, so we should be good. So we just debar it to make it colorful. That's a process of itself. Then we make it again. And that's what we have to change the name because it's not a good name. And we save. Yes. Okay. And done. This is a process and a half, so if anybody has any questions about it, you can put that in the chat, but I think we're ready now. Yep. Okay. That's its name, right? Yep, that's its name. Nice. Those are the argon lines, and now I have to tell it what those are. So those are the same as before, so that's not going to be too hard. So now I just have to find it. It's like 6,532. Hydrogen alpha. And this neon line at 6,598. Nice spectrum. Now give us a spectrum. Alright, we got it. And hopefully now we can take guesses on why this is an interesting star. Anybody want to guess what the meaning of this is? If you notice this, it's pretty noisy, but if you notice, this is a bifurcated spectrum. Now we can match this to an older spectrum here. This same folder. Let's see, where is that? Alright, it's here. So, it's a bit close, actually. Yeah, let's close all of these. Yeah, got it. Let's the graph it spit out. Okay, so it's a little bit, these two different lines are a little bit closer in right now, but in the past they were a bit farther apart, so they're a little more evident. But alright, does anybody have a clue? Let's check the chat. Okay. Oh, what specific make or model? This is called a Lears 3. It's high resolution, which is why it can only see around 20 nanometers or even like 15 at a time. And this is like about $3,000, but you don't have to start with something as high resolution as this. There's cheaper stuff that's much more that shows a little bit more of the spectrum at a low resolution. But anyways, so there seems to be no answer on the chat. So the reason why there's two spectral lines here is because it's a binary star. So there's actually two hydrogen alpha lines from two different stars, and the only way we can tell is because we're seeing it in the spectrum that there's two different lines. And there's a Doppler shift because they're orbiting each other. So the reason why these are two separate spectral lines is because there's a Doppler shift from the stars orbiting each other. So as one goes in one direction, the other one's going in a different direction. We have a different shift, and we can see these lines separate. And how far the lines are apart depends on where in the orbit the two stars are. So in the past, we could see that the lines are farther apart because they're moving faster and faster in our direction, but in the orbit now they seem to be a little bit closer. And what happens is as you monitor the star, these lines go apart, they come together, go apart, come together. It's a cycle, and you can use that to measure what the orbital period is, and it's around, I think, 3 days. So if we come back in tomorrow, if I took this again tomorrow, it would be a much different graph than what it is right now. So that's what makes the star interesting. But if you look at the image of the star, there's not much there you can really see besides it just being a regular blue, really bright star. It's in Auriga. I think it's Beta Aurigae. I'm not too familiar, but yeah, no, you can't separate this without spectroscopy. So that's something that's really cool. Okay, let me see what the next. Okay, we're gonna move on to 8. So that's something that's very cool that's a little bit, even I would say, even more cooler than the star. So let me first head there. Let's find its sequence. Oh, we're gonna have to do meridian flips. Guess I'll be doing that. Yeah, it's usually when you do spectroscopy, you stay on one target for hours. We don't usually do like three or five in one sitting. So, but I think we're there. So let's try to find the star now. Oh, there it is. Oh, there it is. Just missed it. Oh, we're coming back. Okay, well. We go a little bit slower this time. Almost there. No, there we are. So, we got some guide stars too, so that's good. Oh, wrong direction. That, if you're hearing that button sound, that's the hand controller. Yep. Back up. And guide button. Almost there. Guide. Oh, wait. That's good enough. Hopefully. No, that's not good. Go back. You have to get really centered in order to get the highest amount of light. Come on. Okay, there. Procedure and a half. Okay, now we can actually. It's not being aggressive to my liking. It has to get really centered. It's not centered enough. That might be it. No, it's not. Why is this star being so annoying? Oh, let's not do that. Light. Oh. Gotta clear this. And it's almost there. Okay, good. Now we can do that processing step. And let's see. There it is. Debar it. We're gonna make it from mosaiced onto an actual color image. Oh yeah, that looks good. So. grayscale. Oh, we have to. Let me check that down. Let's make this a good name. So let's do that. And let's okay, good SNR. And we have to tell it these spectral lines again for the calibration. So that's going to be the same process as before. 2, and that's 6, 5, 8, 9, oh, 9, 8. Ooh. That would be a costly mistake. Okay, there we got calibration, and now we can finally see what's interesting about this star. Okay, good. So this looks a bit ordinary, but there's a little bit overabundance of these other spectral lines. So what's special about this star is it's actually a really young star. It's a protoplanetary disk. So if Doug went there, yeah. Oh, that's a flaming star. We were supposed to go to that, but we cut that out. Yeah. So, but this is another interesting star. This one is actually, this is 8 It's slightly different. It's not a protoplanetary, but it's actually an O-type star, and this is what's illuminating this blue nebula and this hydrogen alpha. But the target we're looking at is a very young star. It's called a Herbig AE/VE star, and it has a protoplanetary disk around it. So what we get from having this phenomenon is alterations to the hydrogen alpha line. So the way it is here right now, it looks like a pretty normal absorption line. But we also have all of this repetition of that line here, and that's indicating we got dust around the disk. And all of these other extra lines here are metallic lines indicating, all the metals in that protoplanetary disk that we're seeing. So we can derive all of this from just examining these peaks and valleys. But in this case, they're all valleys because we're looking at absorption spectra. That's when these atoms are absorbing the light coming from the star. So I guess if nobody has any questions, we can just go to the final star. I guess we'll go to the flaming star since Doug's already on there, so. Okay, then we'll just basically have to load the sequence. This will be our final target, so we're gonna wrap up after that. And we're seeing it's. Okay, center the start then. There we are. Oh, come back. A lot of button pressing to get it back here. Now we have to do the centering procedure. And I think that's centered, so we're just gonna guide. And now it can actually start taking spectra. Unless it decides to uncenter itself, then I have to do that again. Well, I think that's good enough. We'll just take a... Oh, it's already... Now I can take one. Okay, that's not half guiding then. That's half arc second. Say this is our target here. This is AE array. Not to be confused with the last one, which was AB. And what's interesting about this one is it's got this nebula complex, and it's called a flaming star nebula, because this star here is illuminating all of this gas. It's reflecting its light, and it's also causing some hydrogen atoms to emit, which is this reddish complex you see around it. So we've visited this before on previous star parties, but we're going to be looking at it with spectroscopy. So I'll just let this take that while I'll preset the capture. So if you notice, a lot of phenomenon tends to happen around hydrogen alpha, so it's a very interesting line to look at. It's actually what this spectrograph is designed to look at. Okay, that worked. I'll tuck that away. Okay, we're almost done taking our image, so we just have to open it up and fix Insight. Okay, we got it. Are you there, Doug? You're causing some feedback. And we'll make that grace. I guess we'll keep it the way it is. It's a big long name. Yep. Nope, only two pieces. It's not the best way of calculating, but that is a way. Right? That's I don't know what to make of that. That's interesting. Oh, this is what happens when you don't debayer. I guess this is what I'm. This is a way of showing you that. So what happens when you don't debayer is because you have all these tiny filters, it causes this to happen, where you get all of these little filters causing the spectral line to look like this. Let's let's do that again. But oh no, wait. What happened there? Oh, I left both of them in there. I guess that's what happened. So this is the actual spectrum we're looking for. So just like the before, this time we've got the hydrogen alpha line here, and we've got the metallic lines. But these are not from a protoplanetary disk. This is because it's a very, very hot star. In fact, if it was around here, we're almost cut off the helium line. But what we're looking at here is we've got this big iron line, we've got the hydrogen line, and some various metallic lines. This one's a bit unusual, that feature. But this is a very hot O-type star. This is the hottest classification of stars we have. And this is the star that's at the heart of the flaming star nebula, and that's what illuminates it. So let me check the chat really quickly. So let me ask there. Can you unmute, Doug? So let me wait for that. If anybody has any questions, we're about to wrap up, so this would be the time. Are you there, Doug? Well, I can't quite hear. Hey, he's unmuted. Oh, what's going on here? Oh, it's having trouble guiding on that star. But yeah, it doesn't seem we have anything else in the chat, so. So if you notice how this line is... No, it's echoing now. Well, if you see this is a little slight offset, this can either be due to like the calibration error, or it can be because of the Doppler shift of the star. Okay, well it. Hmm. Hmm. Okay, well. Try to. Well, let me. I guess Doug can't unmute, so we're gonna. So I guess we're gonna end here. Well, if thanks for sticking around for all the technology problems, but I think we got some good data in here, and then hopefully people understood what we're able to do. So thanks for being here tonight, and we'll see you for the next Star Party.